Dear students, today we will discuss on the operation of induction motor when it is supplied with unbalanced voltage or when the induction motor is supplied with non-sinusoidal voltage. How the performance of induction motor is affected, that type of analysis we will try to analyze and solve problems related to that. In the previous class, we have discussed about the torque equation of induction motor, the speed torque characteristics we have seen for various types of squirrel cage induction motor and slip ring induction motor. How the torque can be varied or starting torque can be improved in case of a squirrel cage motor with a double cage or deep rotor or deep cage rotor type. In case of slip ring induction motor, how the torque slip characteristics can be varied by varying the external resistance. Accordingly, we have derived the equation for the breakdown torque or the maximum torque, and we have determined for a numerical example how the breakdown torque can be calculated and the slip of the induction motor can be found. With this torque equation, we will extend the use of this torque equation for our this unbalanced condition state of induction motor. So at the end of the session, you should be able to determine the current and the torque of induction motor under unbalanced condition, particularly the single phasing condition. The unbalanced source operations, if you see, if for example, we have three phase voltages of unbalanced nature, either they have same frequency but magnitude is different. In that case, the unbalanced three phase voltage can be resolved into three components: positive sequence component, negative sequence component, and zero sequence component. Any unbalanced three-phase system can be resolved into three balanced systems. One is called as the positive sequence, second one is the negative sequence, and third one is the zero sequence. So this positive sequence voltage, again there will be three voltages, three positive sequence voltages, one for A phase, second for B phase, and third for C phase. So therefore, this positive sequence phase voltages, they are given by Vp is equal to 1 by 3 into Va plus alpha Vb plus alpha square Vc. Similarly, the negative sequence voltage, where the phase sequence now is ACB. Here, the positive sequence phase voltage, if it is ABC, for the negative sequence voltage, the sequence will be ACB. So here, these negative sequence voltages are given by 1 by 3 into Va plus alpha square Vb plus alpha into Vc. So this gives the RMS values of the positive and negative sequence voltage. Coming to the third one, the zero sequence voltage, all the zero sequence voltages, let us say Va naught, Vb naught, Vc naught, these are in phase with each other, and then the average voltage will be 1 by 3 into Va plus Vb plus Vc. And this term alpha is given by e to the power j 120, or alpha at an, that is alpha at an angle 120, sorry, 1 at an angle 120, and that is given by cos 120 degrees plus j sine 120 degrees. So in case of the unbalanced system, if the neutral connection is not there, zero sequence current does not exist. So zero sequence currents will be there in the neutral wire, and if this neutral connection is not there, this zero sequence components will not be present. So motor performance can be calculated based on the positive sequence and negative sequence voltages. So the resultant performance is obtained by the principle of superposition, that is the assuming there are no nonlinear elements in the motor, so we can combine the effects of positive and negative sequence component and find out the resultant performance. That's what we'll find and derive a effective torque equation. For positive sequence components, as the phase sequence is ABC, similar to that of the fundamental component, and hence the slip S is given by omega ms minus omega m divided by omega ms. So the rotor rotates in the forward direction. So for this, the current is given by what? Voltage, phase voltage divided by the total impedance, neglecting Xm here, the mutual reactance. So IRP dash is equal to Vp at an angle theta P divided by Rs plus Rr dash by S plus J into Xs plus Xr dash. So once we have derived this torque equation in the previous class, there's a current equation. Same here. Instead, here terminal voltage is replaced by positive sequence voltage Vp. That's all. So the TP, the torque produced due to positive sequence voltages or flux, is given by 3 by omega s into Vp square into Rr dash by s whole divided by Rs plus Rr dash by s whole square plus Xs plus Xr dash whole square. So this equations remain same as in the previous condition. Now coming to the negative sequence voltages, as now the phase sequence is ACB, okay, these will produce air gap flux in the opposite direction, and hence as the flux are rotating reverse. Now the slip will be given by what? The synchronous speed is minus omega ms minus the rotor speed omega m divided by minus omega ms. That will come to 2 minus s. So therefore, the IR dash now will be equal to what? Vn divided by Rs plus Rr dash by 2 minus S plus J into Xs plus Xr dash. And this currents will produce torque Tn equal to minus 3 omega s into Vn square into Rr dash by S divided by Rs plus Rr dash by 2 minus S plus whole square plus Xs plus Xr dash whole square. So the equations remain same with change as S is replaced by 2 minus S and the torque is negative because you have omega S here, which is negative for negative sequence voltages. So torque has a negative sign because of negative sequence voltages. The speed is negative minus omega ms. So the RMS rotor current and torque are given by. So there are now two currents, IRP and IRN, current due to positive sequence, current due to negative sequence. These two combined effectively based on their phase difference, the resultant current IR dash will be equal to IRP dash square plus IRN dash square whole to the power half. That means square root of IRP dash square plus IRN dash square. Okay, this gives the resultant rotor current IR dash. And coming here, the torque, the positive sequence torque produces, let us say, in clockwise direction. Negative sequence torque is, let us say, in the opposite direction. Therefore, the net torque is the algebraic sum of this one, Tp plus Tn. Tp will be positive and Tn will be negative. So with that, the effective T becomes smaller than the Tp value. So effective T is minus 3 omega s into all these things. So what is the observation made here? If, for example, we have the motor characteristics like this, the positive sequence components will produce torque speed characteristics like this. The negative sequence components will produce the torque speed characteristics like this between 0 and omega s. Why? Because the positive sequence component torque, if it is extended speed torque characteristics, it will be like this. And if, for example, the motor is running with negative voltage, now the characteristics will be like this. Okay, so this part is the one that we are observing. So the positive sequence component will produce this one, the negative sequence component will produce this one, and hence the net torque will be algebraic sum of these two, and it will be this thick line. Similarly, if you see here under single phasing condition, the net torque is given by this one. So the same thing. There is possibility of becoming zero here. Yeah. So the observation what we are making is that the net torque has decreased, but the current will be increasing. So the net torque has decreased, but the net current has increased. With this, what happens? I square R dash I square R losses will increase. So therefore, what does it mean? Copper losses increases. Copper losses increases and hence efficiency decreases. So as copper losses is increased under unbalanced condition with reduced torque, the more heat is produced. And core losses are the core losses are also increased because core losses are produced due to the flux produced by the positive sequence flux and also due to the negative sequence flux. Therefore, core losses also increased and hence efficiency has decreased. So if the unbalanced is more than 5%, it is not suggested to continue because the motor gets heated up and there is a chance of burning of the motor. Burning of the motor. So with that introduction, we shall see a problem. A 440 volts 50 hertz 6 pole Y connected induction motor has the following parameters per phase referred to the stator: RS RR dash 0.3 ohms, XS XR dash 1 ohm, and XM 40 ohms. Normal full load slip 0.05. Supply to one phase of motor is disconnected. That means unbalanced condition. So calculate the motor current and torque as a ratio of full load values for the full load speed. Yeah. So for normal operating conditions, first you find what is the synchronous speed that is coming to 1000 rpm, and in radians per second omega s is given by 104.76 radians per second. So full load current IR dash. So we can use this formula V divided by the impedance RS plus RR dash by S plus J into XS plus XR dash. So substituting the value and solving, you will get IR dash as 38.43 at an angle minus 17.61 degrees amperes. So the motor current, what is motor current? That is nothing but stator current, which is rotor current IR dash. As in the problem, XM is given, we have to calculate that magnetizing current also, because the rotor, the induction motor equivalent circuit will have XM parallel like this, and stator impedance, rotor impedance. Okay. So this we have found, that is IR dash. Let this current be IM. So we have to find IM, then we'll find the total current IS, supply current or the motor current. So by adding IR dash and IM is nothing but what here? IM is nothing but this voltage, phase voltage divided by XM. So 440 by root 3 is the phase voltage divided by XM, that is 40 at an angle 90 degrees. Solving, you will get IS is equal to 40.8 at an angle minus 26.14 degrees amperes. So the torque developed by the motor, once we find that one, we can find the torque T is 3 by omega ms into IR dash square into RR dash by S, and solving you will get 276.01 Newton meter. Now, when one supply is removed, that is motor is operating under single phasing condition, then we have to calculate forward impedance, backward impedance. Why? Because the slip is changing. So ZF will be equal to what? RS plus XS plus this thing. Then you will get the forward impedance as 5.89 plus J 2.79. Similarly, under backward impedance for negative sequence components, the backward impedance is given by this one, the total impedance. The S becomes now 2 minus S. That's all. The remaining things remain same. And ZB is 0.45 plus J 1.98 ohms. Adding ZF plus ZB, you can find out what is the total impedance of the induction motor. So now, under that open circuit condition, by combining ZF and ZB, we have got the equivalent Z. So from that, we can find current. I is equal to V by Z, that is 32.03 amperes. And TP, positive sequence current, positive sequence torque. We have seen this formula, 3 by omega ms, 3 is written here. So that is 164.26 Newton meter. And negative sequence torque is given by minus 4.3 Newton meter. So the net torque is TF plus TP plus TN, and that comes to 160 Newton meter. The observation here is like, see, the torque initially was 276, now it has become 160. So the net torque has decreased. Current in this case, the initial current was 40. Now the net current in this case here it is 32.03. So it is safe and you can run the motor, not an issue. If this current is becoming more than the rated current under normal condition, then you have to see that the single phasing operation should be stopped and motor should be stopped. Okay. So now coming to operation of induction motor under non-sinusoidal conditions. The supply voltage is not sinusoidal. It is not sinusoidal like this. There may be some distortions like this. So this, you know that any non-sinusoidal component can result into number of sinusoids which are integral multiples of the fundamental component. I can resolve this into number of components. All are sinusoids by using what? By using Fourier analysis. So this component which has same frequency as that of the supply is called as the fundamental component, and the remaining are harmonics. So what is the observation here is, for a three-phase induction motor, either star or delta connected, the triplen harmonics are not present. Triplen harmonics means what? The multiples of third harmonic, 3, 6, 9, 12, 15, they are all absent. So, and as the assuming that the supply non-sinusoidal is symmetrical, then the even harmonics are also not present. Only odd harmonics are there. So 3 is not there, 4 is not there, 5 will be there. Next 6 is not there. So therefore 7. Next 8 even number. So it is not there. 9 is not there. Next 10 even number not there. 11. Okay. 12 not there. 13 yes it will be there. 14 even number no. Next 15. Like that if you see, you can find the fundamental component in each phase which are lagging by 120 degrees, and similarly let us say fifth harmonic component and seventh harmonic component. Out of this, the lowest order harmonics are fifth and seventh, which cause more effect on the performance of induction motor. As the frequency number increases, the value of these voltages magnitude is very small and can be neglected. So the observation, if you see here, you have here VA at an angle 0, VB at minus 120 degrees, and VC is minus 240 degrees. So if you see fifth harmonic component, you have here VAN is at 0 degrees, VBN, fifth harmonic component, see fifth order frequency, fifth harmonic component is lagging by 240 degrees, and VC is by 120 degrees. So the sequence will become what? A, C, B. Okay. For seventh, it is A, B, C. So you can observe that fundamental has sequence ABC, fifth harmonic has ACB, seventh harmonic has ABC. So in general, harmonic voltages of the order 6K plus 1 have positive sequence, and 6K minus 1 has negative sequence flux produced, and hence the negative sequence stops. So the observation what we can see is, when harmonics are increased, there is increase in the value of RMS value of current. Why? Because RMS value there is for fundamental, and harmonics are also having RMS value. So the effective RMS value is more than the fundamental component. So harmonics are increased. Increase in resistance and skin effect. So because of increase in the RMS value of current, the stator and rotor windings gets heated up, and hence resistance will increase. Rotor and stator resistance will increase, and that will cause a skin effect. So increase in copper losses because I has increased, R has increased. Increase in core loss because of flux produced by the harmonic currents. Then derating of motor, as the motor is getting heated up and losses are more, so you have to operate the motor with less power than the rated value, so you are derating the motor. Then reduction in efficiency has decreased, and pulsating torque. Fifth harmonic component will produce the torque oscillations, seventh harmonic will produce torque oscillations. The net torque will be pulsating one. Yeah. So in summary, what is that we have seen today? We have seen the equations of rotor current, power, and torque of induction motor with the single phase operation, and operation of induction motor with non-sinusoidal supply, which is resulting into pulsating torque and motor derating. So dear students, by now, as per the problem that is solved, you should be able to determine the current and torque of induction motor under single phasing condition. Yeah, try to refer these questions and answer. what is single phasing, why it should be avoided, what are the disadvantages of induction motor operation with unbalanced supply voltages. Okay. So one more problem is given, so you can refer this one. So further, we can, for understanding still incomplete, refer chapter 6, section 6.2 and 6.4 from GK Dubey, and try to go through the solved problem, and also solve the exercise problem 6.1. Thank you, students.